Hello, everyone. It's my pleasure to have been invited to talk at Construction 4.0 event by ConTech. I'm Hélène Lombois-Burger. I'm heading the R&D on digital fabrication at LafargeHolcim, and I will just discuss with you recent material developments we made for concrete 3D printing, and I will illustrate this through recent large-scale job sites that we did with our partners. So our belief is that 3D printing is to be used when it brings an additional benefits versus reference construction technologies. And we see four main benefits. The first one is the material efficiency. You have the ability to place exactly the right material at the right place. So it means that you can save up to 60%. You see here an example of a bridge application by a Dutch startup. But you have plenty other projects of bridges. I will just show a few ones. And they all land on the same figures typically. The second one is to have the ability to increase the construction speed and productivity. Construction is suffering a productivity gap. It's one of the industries that has less enhanced its productivity since World War II. And with 3D printing, you have the ability to print and to build up to twice as fast. The third one is the flexibility and scalability. You can make some mass customization without any overcost. You have not to amortize a mold over large series, so you can do one-off designs without extra cost. And the last one is the ability of reduced logistics for large parts to avoid the transportation of pieces larger than 4.5 meters, usually difficult on road. Beyond this, you have additional ones, be it in terms of health and safety or whatever. And the way we do it is that we try to work in an open innovation approach to address the whole value chain. Indeed, the design should be application and manufacturing informed. Instead of having something that is sequential, you will just deal with everything at the same time. And the development path starts from the application. You will decide what you want to print. Is it a bridge? Is it a wall? Is it a slab? Then you will pre-design. You need to review your design for 3D printing to optimize it. Otherwise, if you just copy-paste usual designs, it will never fly. Then you will select the print technology, the best suited for your application. If you want, for instance, a large volume, it's better to have a gantry. If you want to make some very complex shapes, it's better to have a 6-axis. And then you will develop the material to have something that copes with the specifications from the application, the design, and the manufacturing technology. You have a few key challenges associated to 3D printing. The first one being the fresh stability. You will have some slender structures, narrow and tall, no formworks to support them, and you don't want your layers to collapse when you deposit the upper ones on the lower ones. Second one is related to reinforcement strategies. Usually concrete is working in association with steel. In the case of the extrusion 3D printing, it will be a little bit more difficult at the beginning. So you have some strategies to just include these steel reinforcements. You want to have a monolithic material. It means that you want to avoid cold joints. Cold joints is a brittleness in between two successive layers. If you took too long to print the upper ones on top of the other ones, and you will have some remediation solution to this problem. Next, you want to be robust. Whatever your environmental conditions, be it cold or hot, with a high moisture content or low one, you want to have something that will produce the same printed structure and that will be crack-free. And last but not least, you have an emerging technology and you want it to be included into construction codes, which means that you will tend to develop some parametric models to just make it easier to get your design accepted, typically. So LH has developed two main products in its material offer. One is what we call one-component materials. In that case, you mix a dry mortar or dry material with water, and after mixing, it's directly printable. In the second case, what we have is a two-component material. In that case, you make a first mixing of the dry material with water to have something fluid, which means that it's easily transferable, pumpable. And it's only in a secondary mixing step that will occur in the printing head, typically just prior extrusion, that you will add the secondary component, giving you the printability behavior. That second way is more flexible because you have the possibility to adjust materials property on the fly, but it requires a specific nozzle, allowing you to just get this printable mix. The solution we have developed encompasses various options, be it in terms of strength, from low strength, 15 MPa, to high strength, 90 MPa, or be it in terms of maximum aggregate size. In case you would wish to focus on aesthetic properties, you will have rather micromotors. If you have a limited width, you might go to motors to improve your environmental footprint. And if you have wider elements for still a further enhanced environmental footprint, you will go up to concrete, and this will require some specific process solutions. And last but not least, LH has focused on extended production robustness. We want to allow you to have long production runs without clogging, no need to clean everything in case of production arrest, and to have the same printed structure, whatever the environmental conditions, meaning that it can be cold, it can be hot, you can have some slight wind, middle wind, whatever. Just a few examples to illustrate what is possible. This example is a co-development we are making with General Electric Renewable Energy and with manufacturing some wind turbine towers, and Cobod, who is a Danish startup offering a gantry printing. The idea is to increase renewable energy production using making taller towers with larger bases and bypassing logistic constraints to transport these large bases thanks to printing on site. These taller towers will allow you to harvest more efficient winds, typically. We made two prototypes. The first one that you see here is the one done in October 2019, in which we wanted to demonstrate the ability to print at height. So it went up to 10 meters high, typically. And a second one that we did last October, in October 2020, going towards structural design. So it's another design to just have the ability to be structural, typically. And in that case, what we are developing as a material is a one-component concrete, high-performance one, and with the aim to just reach some very large throughputs and be robust to on-site environmental variations, temperature, wind, sun, that can just generate some temperature gradients, and so on and so forth. The second example is related to affordable housing. It's something that we do with 14 Trees, which is a joint venture between LH and CDC, and still with Cobod at the printing company. What we target here is a faster construction. Malawi is suffering a backlog of 36,000 schools, and it will require over 70 years with conventional construction methods to bridge it. With 3D printing, it could be possible in only 10 years' time. The solution was labeled by Solar Impulse, both for its environmental impact and reduction of carbon footprint, but also for its economical viability. Two prototypes were printed in November 2020 in Malawi, one of a home that you can see on the left, in which you have, you can't see it on the picture directly, but it's a double layer in that case. And on the right, you see a prototype of a school that was printed a few weeks afterwards, trying to further improve the environmental footprint, going towards a single layer wall to have something that is nevertheless still stable. We have no use of the cavity wall, as no formal installation is required in that case. And so we developed a specific design with a crenellated shape that allow you to furbish properly your building, to have new functionalities and have something that is stable. We had to cope with very high external temperatures and control the curing typically. And in that case, what we use is a one component mortar with, I would say, lower throughputs than with the wind turbine tower application. And still, we need to just manage on-site printing conditions. I will just show you a short video about west printing. So you can see the slab on which the home is printed and the gantry printer. With the mortar that is printed, you see here clearly the double layer design. And you see that the robot was piloted by local people, as you may see. It was printed typically at night because the temperature was so hot that we had to do it at night. You had just sent the connectors in between the two layers typically that were made. And it's also included some other products from LH. And so now I'm going to discuss about first project of bridge that we had. It's a bridge that is intended for Paris Olympic Games 2024. In that case, as I mentioned earlier, what we target is to have better efficiency in terms of material savings. With up to 60% of material savings because we optimize the cross-section of the bridge, putting the largest parts only when needed. So the consortium won this tender in 2020, and the ongoing phase on R&D is intending to optimize the interaction between the material and the process. And to just improve the materials to decrease still further the environmental footprint. So in that case, given the complexity of the shape that we have with a honeycomb shape that could never be produced without 3D printing, what we leverage is a 6-axis robot, which means that what we use is a high-performance 2-component mortar because we want to produce these very complex shapes, and we have some quite enhanced aesthetic requirements. You may see here the renderings done by the architects typically. The last project is a second project of bridge, Pedestrian Footbridge, that will be displayed at the Venice Biennale this July. So this time, once again, we optimize the material use. Thus, the design is based on masonry, and the idea is to use this time the bridge in compression only. The former bridge, you will use post-tension to get the required load-bearing ability. In that case, you have no steel anywhere, just the printed 3D printed mortar. And the blocks will be assembled dry stacked, which means that you have the ability to disassemble the bridge if you want to have a circular element. You can reuse the bridge somewhere else. So the project was announced last May and will be just displayed, as I was mentioning, this July. And in that case, once again, what we were using is a 2-component mortar. You can see that we have some large overhang parts. So it's very important to get this 2-component to have the ability to just get these overhang parts. With very high aesthetic requirements, and the way it looks is like ceramic typically on the surface. And that's it. It was really my pleasure to be invited to this Construction 4.0 event by ConTech, and I hope you enjoyed these elements about 3D printing of concretes.